When someone asks why a prediction happened and you only have an accuracy number, trust in the model drops fast. We will compute feature importance in Python so you can point to the signals driving decisions and spot broken patterns early. You have a model that gets reasonable scores, but you still worry. Which inputs matter? Which inputs are masking a data leak? After this video, you will be able to rank features, compare simple and regularized signals, and explain a single prediction in a human-friendly way. No heavy math, just intuition and practical checks you can run in minutes. I'm Professor Pi, teaching AI foundations, from basics to advanced, with simple concepts-first Python that helps you solve bigger, real-world problems. Now let us build a tiny pipeline that shows risks and remedies. This snippet trains a tiny linear model and reports how well it fits. It fits a small dataset with a few engineered features and a numeric target, so you can see signal strength directly. The key idea is to use a linear baseline because coefficients are readable. The snippet shows training and a simple fit metric on held-out data, so you know whether the model learned anything. If the fit number is low, nothing below will be meaningful. If it is high, coefficients become useful as first-order explanations. A tiny dataset keeps the story clear and lets coefficient signs and magnitudes be visible. Next, we will sort the model weights to see which inputs look important. This snippet ranks features by the absolute size of their coefficients. The main point is simple. In a linear model, a larger absolute coefficient means a feature moves predictions more per unit change. The code takes the trained model weights, maps them to feature names, and sorts by absolute value. You will see both positive and negative influence, but the ranking ignores sign to highlight magnitude. Remember that coefficient size depends on the feature scale. If a feature is large by scale, its coefficient can be small and still matter. Scaling features changes these numbers, so we note whether inputs were standardized in the first snippet. Next, we will measure raw single variable signal using correlation. This snippet measures raw signal by correlation and ranks features. Correlation here is the Pearson correlation, which measures linear association between a single feature and the target. The code computes correlation per feature and then ranks them by absolute correlation to show which inputs individually track the outcome. This is a quick sanity check and may highlight features that the linear model missed or downweighted. Correlation is blind to multicollinearity and confounding, so it can overstate importance when two features carry the same signal. Use this as an early diagnostic, not the final verdict. Next, we will stabilize importance by adding a regularization term. This snippet applies L2 regularization to stabilize feature importance. L2 regularization penalizes large coefficients and shrinks noisy weights towards zero. The code retrains the same linear model, but with a positive regularization strength so that unstable, high variance coefficients are reduced. The practical effect is clearer rankings when features are correlated, or when you have more features than data. Choosing a larger regularization strength increases bias and reduces variance. Choosing a smaller value keeps the original coefficients closer to the unregularized model. Watch how the ranking and absolute sizes change between the two models. Next, we will explain a single prediction by breaking down contributions. This snippet explains one prediction with per feature contributions. The idea is to decompose the model output into the sum of a baseline plus each feature's contribution. The code computes the baseline prediction and then multiplies each feature value by its coefficient to show how much that feature pushed the prediction up or down. HIS produces a ranked list of contributions you can read to a stakeholder. It highlights which inputs drove a specific decision and whether any single feature dominated. Use this when you need a quick, local explanation for audits or troubleshooting. To map this toy to a real project, swap the tiny dataset for your modeling set. Keep the same checklist and add a validation step that compares coefficient rankings to domain expectations. If a domain expert expects two features to be top drivers, but the model says otherwise, investigate data leakage, target shift, or missing pre-processing. Recap. First, feature importance gives a human-readable view of what the model relies on. Second, use coefficient magnitude, correlation, and regularized coefficients together to cross-check signals. Third, one caveat. Raw rankings can mislead when features are correlated or on different scales. Next step, run the same pipeline while tuning the L2 regularization strength and compare rankings across 3 values to see which features remain stable. That stability check is the strongest signal for trustworthy importance. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.